Here we are. We're going to look at the June 2018 Part B-2 questions. And I'm so glad you're here because a lot of times students will do some multiple choice and they'll never get around to practicing Part 2 questions. They're just as important as the multiple choice. So let's go ahead and get started. Okay, so what happens here, of course, is you're going to have an answer booklet and you're going to write your answers in the booklet. I'm just going to go from the test because it's easier to do it this way than to flip back and forth. So in question 51, it says to state the general trend. So general trend, we're looking for first ionization energy as the elements in period 3 are considered from left to right. Okay, so hopefully you remember what first ionization energy is, and you really don't need to know the definition here. You need to remember either the trend itself or to look it up on reference table S. But ionization energy, well, first ionization energy means that I have any element as a gas and I'm going to shoot it with some energy, knock out the outermost electron, and make that atom an ion. How much energy? Well, that's first ionization energy. So let's go and take a look at the periodic table first, pick out some elements in period 3, and then go to reference table S. Okay, periodic table, we're looking at period 3, and we're just going to pick a couple of elements. Let's say sodium. Now it says general trend. So you don't have to look up every one, but you don't want to look up ones that are just very close because we're just looking for trends. So let's say maybe sodium, aluminum, maybe sulfur, and argon if you want. I don't even know if we have to go that far. So let's go to reference table S. Okay. Okay, that was the answer for 51. Let's go to 52. Identify a type of strong intermolecular force that exists between water molecules but does not exist between carbon dioxide molecules. Now, there's a little basket of molecules that you need to know the structures for and whether or not the molecules themselves are polar or non-polar. As it turns out, water is a polar molecule. It has polar bonds and is a polar molecule. Here is the Lewis structure. We say that the shape is a bent shape, and it's such a strong polar molecule because it has hydrogen bonding to oxygen that the type of attraction between one water molecule and another is known as hydrogen bonding. So there's your answer. Now, carbon dioxide is a nonpolar molecule. You have a linear molecule with a carbon double bonded to an oxygen on both sides. Now, oxygen does have some excess electrons, 4 as a matter of fact, which I'm kind of trying to put in here. Not doing a great job. It is a linear molecule. So carbon dioxide, while the bonds between carbon and oxygen are polar, it is a non-polar molecule. So what was New York State looking for? That you said hydrogen bonding or dipole-dipole forces or dipole-dipole attractions. All right, let's go to 53. For 53, we have to draw a structural formula for 2-butanol. Now, there are some reference tables with regards to organic chemistry, so let's go to it. Okay, so there are 3 organic tables. As a matter of fact, the first one here has to do with prefixes. So we were looking at 2-butanol. So you see but is 4 carbon atoms, and we keep going. Now we have an OL ending, so we're going to pass this. It's not an alkane, or an alkyne. We need to go to reference table R. And what we're looking at here are the alcohols. How do I know that? Because of the OL ending. So 2-butanol, and you would do this for any molecule for organic when you got to draw it. The OL ending tells me I have an OH. But means 4 carbons, and the 2 tells me where that OH is going to be. In other words, draw your 4 carbon chain, and I'm just going to count from left to right. I'm going to make this the second carbon. It does not matter whether you put the OH above or below, but now we have to fill in the carbons with 4 bonds. So if I start on the left, I have 1 bond already between one carbon and the other, but now I'm going to fill in the other 3 with hydrogens. The second carbon has 1 bond with the OH, 2 on either side with carbon. It just needs 1 more. The third carbon, I need an H above and an H below, and the last 3 H's again. So here is the structural formula for 2-butanol. That was question 53, and now we're on questions 54 through 56. All right, so with 54 through 56, we have this table of information, and 54 explain in terms of element classification why silver chloride is an ionic compound. Well, you want to remember ionic compounds. You have a metal and you have a nonmetal. In this case, silver or Ag is my metal, chlorine or Cl is my nonmetal. And that's what they were looking for. So element classification. Don't forget there's a third group. Those are your semimetals or metalloids. Make sure you know where they are on the periodic table. Memorize them. All right, for 55, we're doing a numerical setup. What that means is we are going to plug the numbers into an equation. We don't have to calculate the answer. We just have to show the work. All right, so percent composition by mass of silver in silver carbonate, and they give us the gram formula mass. There is the percent formula on reference table T, so let me show you that. So here it is, percent composition. The part is going to be our silver, and the whole thing is the gram formula mass, and they even gave us the number. Now, don't take anything for granted when you are practicing or studying for the test, or for that matter, taking the test. Look up the equations on reference table T. Even though you think you know the trend, double check by using the periodic table and reference table S like we did already in this section. You don't want to make a silly mistake. You want to minimize, you want to do the best you can. And you're taking the time to do it now, so do it the day of the Regents exam. Okay, so for 55, I'm just going to put it up here. Percent is equal to, the part is the mass of the silver. Now be careful, silver carbonate, here's the formula. I'm sure there's tons of kids that just put in the gram formula mass for silver, but did not multiply it by 2. But that's exactly what you have to do. The gram formula mass for silver is 108, and 108 times 2. You don't even have to multiply it out, right? We're just showing a numerical setup, and that's the part. And then the whole thing is the silver carbonate, and they gave us the denominator, the 276. Don't forget, this is percent, so you have to multiply by 100. And there's your setup. All right, let's go on to 56. And these three, identify the silver compound in the table that is most soluble in water. All right, so we need to go to the reference tables and look at what is soluble versus what is insoluble. So we have these 4 compounds we're going to take a look at. More specifically, we're going to go ahead and we're going to look at the formulas. At reference table F, I wrote down the compound formulas again. Before I use reference table F to figure out whether it's soluble or insoluble, remember we're looking to split these formulas, because the way that reference table F is written, we're looking for the positive and the negative ions. So let's just start with the first column. We don't see silver written. I go to the exceptions. So it goes from soluble, the exceptions, these are the insoluble compounds. And look what's an exception, silver. So silver chloride is insoluble. That's not going to be our answer. We're looking for what is soluble. Another one is silver with sulfate. That is in the exception column, so that is also insoluble. But if we take if we go back up to chlorate, there are no exceptions. So that's probably our answer. Silver chlorate is going to be soluble in water, but let's just double check. Carbonate is not here, but carbonate is here. Ions that form insoluble compounds. Silver is not an exception, so again, it is insoluble. That makes our answer the silver chlorate. Okay, we're on to questions 57 through 59. We're told that cobalt-59 is bombarded by a subatomic particle. We get a radioactive cobalt-60 atom. After 21.084 years, 1.20 grams of the original sample produced remains unchanged. Okay. 57. Complete the nuclear equation by writing the notation for the missing particle. That means that this is on your answer sheet, so let me call that up. Okay, so here you see question 57. And when I balance nuclear equations, it is really easy. The mass numbers are the numbers on top, have to equal on both sides of the arrow, and the atomic numbers on the bottom have to equal on both sides of the arrow. So I have cobalt-59 here on the left, and I have 60 on the right. What number plus 59 gets me to 60? That's the number 1. And then I have 27 on the left and 27 on the right. They're equal, so it would be 27 plus 0. So I'm looking for a particle that has a mass of 1 and an atomic number of 0. Now, don't guess. Sure enough, there's a reference table for this too. So here it is, the symbols used in nuclear chemistry. And check it out. We have, remember, it was a mass number of 1, atomic number of 0, and lo and behold, it's a neutron. So that's the missing particle you would put on the line on your answer booklet. All right, let's go back to the test. For question 58, we need to go to table N, and it's asking us to identify the decay mode of cobalt-60. Okay, so cobalt-60, I find that on reference table N, and sure enough, here's my decay mode right here. That is beta decay, or you could just put the symbol with the minus sign and say, that symbol decay, right? Just as long as you indicate that, you have your answer for that. Finally, with question 59, we want to determine the mass of the original sample of cobalt-60 produced. So we have to go back up here and notice what we have. We have the total time that's elapsed. And in that time, we only have 1.20 grams of the original sample that remains. It doesn't mean the rest disappeared. It means it was formed into a different isotope. But how do we figure this out? This is our classic half-life problem. So I need to take my total time. I need the half-life for cobalt-60. Yes, that means I got to go back to table N, and I can figure it out. Okay, so I'm going to need my half-life for cobalt-60, which is the 5.271 years. And let's bring that back to the questions. Okay, so half-life problems, they show up pretty much on every Regents exam. Your teacher might have shown you a different way than what I'm going to show you here. It doesn't really matter as long as you're getting to the right answer. But let's take a look. So one of the things I like to do when I can is use some sort of equation. And what I can look at, or I'm going to write down, is the number of half-lives is equal to the total time elapsed over this T1 half, which is that half-life that we got off a reference table. In other words, we have 21.084 years divided by 5.271. And we can figure out from that how many half-lives we got, which I can pretty much see. But you know what? Let's do it the right way. Use your calculator have it handy. Don't do it the wrong way and just say, yeah, I got it, because you might not when it comes to the test. Sure enough, when you plug it in, you get 4 half-lives. Okay, so now I'm going to show you how to do that, but I'm going to go ahead and clear this so you can see it. All right, so we have 1.20 grams remaining. All right, 5.271 years before that, we had double. We had 2.4. Another 5.271 years before that, we had double of that, which is 4.8. See what I'm doing? So when we talk about a half-life, it's the time it takes for half of the sample to have decayed into a different isotope. So I'm going backwards here. All right. So 5.271 years prior, 4.8. If I double that, that's 4.8 times 2 now, was 9.6. And finally, I need one more. Okay, if I back it up, 9.6 times 2 is 19.2. And that's your answer. So notice 1, 2, 3, 4 half-lives. Okay, so 19.2 was the mass of the original sample. That's a little tough because you're going backwards as opposed to forwards. No matter how you want to tackle a half-life problem, you will see it again on the Regents. Okay, here's the next page for B-2. 6 questions to go on this page, and we're off to the final part. So let's do it. Okay, for 60 through 62, we have a heating cooling curve. Of course, this is a cooling curve because temperature is going down over time. And we're starting as a gas because that's what they're telling us. We're starting as a gas. So first thing you're going to do before you answer any questions is label the diagram. Let's put the phases on there. So we're starting with a gas, then we have gas to liquid, liquid, liquid to solid, and then solid. Okay, remember temperature is a measure of the kinetic energy of the particles. So we're going to use that hand in hand as well. All right, let's take a look. So question 60, determine the number of minutes that the substance was in the liquid phase only. See how easy it is now? It's right here. Started at 6, ended at 11. So 11 minus 6 is 5 minutes. All right, that was awesome. Let's go to 61. Compare the strength of the intermolecular forces within the substance at 180 degrees Celsius to the strength of the substance at 120. Well, let me clear this for a minute or erase it. And let's look at 61 again. So at 180 degrees, we're right here. The substance is in the gas phase. And what do we know about particles in the gas phase? They have a lot of space between them. The intermolecular forces are going to not be as strong as liquid or solid phase. And if we look at 120 degrees, we're right here in the liquid phase. So the strength in the liquid phase, which is 120 degrees Celsius, is going to be stronger than the strength of intermolecular forces at 180 degrees Celsius, which is the gas phase. All right, let's go to 62. Describe what happens to the potential energy and the average kinetic energy of the molecules in the sample during interval DE. So DE here, we're at a plateau. What that means is, since we have a horizontal line, temperature is remaining constant. That means kinetic energy is constant or stays the same. But what's happening here, remember, this is a cooling curve. So the temperature is decreasing. We're pulling the energy out. So potential energy decreases. Okay, so again, kinetic energy stays the same or is constant, and potential energy decreases. Let's move on. Here we are with questions 63 through 65. We have a movable piston, 16 grams of oxygen gas, and here's our temperature, pressure, and our volume, which are the same numbers here in the picture. All right, so 63, determine the number of moles of O2 in the cylinder, and we're given the gram formula mass. Now, reference table T is going to have the mole equation. You're looking at reference table T, and you're looking for moles. Now, do not get confused. Mole calculations, we have moles is equal to mass over gram formula mass. And we were given the gram formula mass in the problem, and we're looking for moles. That's the equation that we need. Sometimes students, though, will get confused, and they're looking for moles, and they find this equation. It is a concentration equation. We weren't given molarity, we weren't given liters. So even though we could solve for moles with this equation, it's not appropriate here because we don't have that information. All right, so let's go ahead and calculate moles. So moles is equal to mass over gram formula mass. So we have a mass of 16. So it's 16 divided by 32. Plug it into your calculator, please, and then it's 0.5 moles. All right, for 64, state the changes in both pressure and temperature of the gas in a cylinder that would increase the frequency of collisions between the oxygen molecules. Well, if I want to have more collisions here, I'm going to go ahead, I'm going to increase the temperature because increasing the temperature increases the kinetic energy. And I'm also going to increase the pressure because by increasing the pressure, it's going to squeeze those molecules together. Now, if you thought high temperature, low pressure, that's an answer for a different question. So here in 64, we wanted higher temperature and higher pressure. What you were thinking about is when any real gas is closest to an ideal gas. And you could also get confused because they're talking about frequency of collisions, which we know as the collision theory, right? And that has to do with reaction rates. But there's no reaction here, it's just oxygen in a cylinder. So this is one of those questions where we've got to be really careful with the wording. So the answer, high temperature and high pressure. Okay, one more and we're done with B-2. For 65, we're showing a numerical setup. So that means we're just plugging in the numbers to calculate the volume in the cylinder at 265 and 1 atm. There is only one gas law equation you need to know. It's on reference table T. Let's go find it. Let's plug in the numbers and go on to part C. Reference table T. I'm going down my list and there it is, the combined gas law, right? I have initial conditions for pressure, volume, and temp, and then final conditions. That's what I need back at the question. Okay, so I put the equation here so we could easily plug the numbers in. Initially, we have the values here. 0.5 atm is my initial pressure, my initial volume, 24.5 liters, my temperature, 298 K. On the other side of the equation, I'm going to go ahead, I'm going to plug in for pressure and temperature, and V2 is going to be what we're looking for. So my new pressure is 1 atm. I'm looking for V2. And below, the new temperature is 265. Now you don't need to put the units with the numbers, you're just showing a numerical setup, so the numbers is fine. You don't have to calculate anything, just leave it the way you see it, and you'll get credit. This ends part B-2, and good for you that you went through this part. On to part C. Keep working hard, and good luck. Don't forget to hit the like button. If there's anything that you're looking for me to explain with any of the Regents topics, go ahead and just add a comment below, and I'll do my best. Thank you so much for watching.